Hey guys, what's up? We're up back with day 75 here after a big test today. Today we're looking at applications of the fundamental theorem of calculus. Just as a reminder, again, there are two parts of the fundamental theorem of calculus. We've only learned one part. We're going to look at that one part again. So if we remember, here's what, and again, FTC is for fundamental theorem of calculus. So here's what we remember. It said let f be any antiderivative of, so let capital F be any antiderivative of lowercase f, then the integral from a to b of f of x dx must equal the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay. So that's kind of what we used to help us solve these definite integrals, right? We find an antiderivative, we plug in b, we plug in a, we subtract the two. Okay? But I just want to show you a powerful use of this is rewriting this equation. What we were trying to figure out so far is we were trying to figure out the value of this definite integral. Okay? But now we're actually going to be trying to figure out this capital F of b. Oftentimes they write questions that want you to solve for capital F of b, or the equivalent of capital F of b. So what I want you to do is I want you to solve this equation for capital F of b, meaning I want capital F of b alone. Well, it's really easy to get capital F of b alone. I can do that by adding capital F of a to both sides. All right, so and what I get is capital F of a plus the integral from a to b of f of x dx equals capital F of b. Let me show you what I mean by this, and I'm going to show you an example. I'm going to show you how to solve it in a different way that also works. And there are advantages to both methods. So here's what we know. Capital F is an antiderivative of f. We know the function f is 6x plus 2. Okay. We also know, what I want you to do is I want you to find capital F of 4. Now right now there is no way that I can find capital F of 4 because I don't know which antiderivative it is. Right? There are infinitely many antiderivatives of 6x plus 2. If you think about that, like the antiderivative of 6x plus 2 would be 3x squared plus 2x plus c, right? So depending on what c is, I don't know what c is, so I don't know what f of 4 is going to be. So in order to solve this problem, I need to know another point on capital F. So I'm going to say given capital F of 1 equals 7. So there's another point on capital F, so we will be able to solve this. Okay? So what I want you to think about is think about the fundamental theorem of calculus, right? We know that the integral from 1 to 4 of f of x dx, little f of x, has to be capital F of 4 minus capital F of 1. Okay? This 1 is our A, this 4 is our B. Okay? So here's what we know. We know this. Right? That's just the fundamental theorem of calculus rewritten. Well, here's what we know. Plugging in our A's and B's here, we know capital F of 1 plus the integral from 1 to 4, right? 1 was our A, 4 was our B of f of x dx must equal capital F of 4. And that's what we're trying to solve for. Now we know capital F of 1, we know this right here, equals 7. So 7 plus the integral from 1 to 4 of our function, and instead of writing f of x, I'm going to write 6x plus 2, so that's what f of x is. That's going to equal what I'm looking for, capital F of 4. Now I can figure out what capital F of 4 is by doing 7 plus the integral from 1 to 4 of 6x plus 2 dx. What I call this is, I call this thing my initial condition. And what I call this topic is initial condition plus. Because we do initial condition plus the integral to get our other point. So here's what we're going to have. Solving this thing, right? I'm going to do the antiderivative of 6x plus 2. I'm going to bump the power up to 2 and divide by 2 to get 3. Plus, I'm going to tack on an x to 2. And I'm just going to solve this thing, and this is going to eventually equal what f of 4, the goal of this whole problem, was. Just like when we factored out a number before, when we have the 7 plus in front, we want to keep writing 7 plus over and over again so we don't forget about it. Okay? So 7 plus, now I'm going to plug in 4. And I'm going to subtract this function evaluate, this antiderivative evaluated at 1. Okay. 4 squared is 16. 16 times 3 is 48. So I got 7 plus 48 plus 8 minus 3 plus 2, which is 5. 48 plus 8 is 56. Minus 5. 56 minus 5 is 51. Notice I keep writing 7 plus until the very end, and I get an answer of 58. Okay, so using initial condition plus, I get an answer of 58 for capital F of 4. Let me show you another way that you can do this. Okay? Here's what we know. We know F is an antiderivative. We know that F is an antiderivative of lowercase f, right? And we know that f of 1 equals 7, and we're trying to find capital F of 4. That's our goal. Let me show you another way you can do this, right? Again, f of x is 6x plus 2. I'm going to try this a different way and see if I still get 58 as the correct answer. What I'm going to do now is to get an antiderivative, I'm going to do an indefinite integral. So I'm going to integrate indefinitely 6x plus 2 dx. Now when I do it this way, right, I get what for an answer? Well, again, the antiderivative is the same. I've got x squared, 6 divided by 2 is 3, plus 2x. But when I do an indefinite integral, I always have plus c at the end. Okay? So what I know is that cap f of x is 3x squared plus 2x plus c. Now, I can figure out what c is because I know that f of 1 is 7. So I'm going to plug in 1 for x. And when I plug in 1 for x, I get a y value of 7. Well, when I do this, watch what happens. I get 7 equals, I got 3 plus 2 plus c. I got 7 equals 5 plus c, so c must equal 2. Now I figured out the exact antiderivative that I have. So capital F of x must be, take a look, it must be 3x squared plus 2x, and instead of writing plus c, I now know that c is 2 plus 2. Now I can find f of 4 by just plugging in 4. And 4 squared is still 16, times 3 is still 48. And 48 plus 8 is 56. And lo and behold, 56 plus 2 is 58. So I still get f of 4, capital F of 4, equal to 58. Whether, and again, I got that, whether I used initial condition plus, or whether I found the antiderivative plus c and plugged in to solve for c. Okay? Now, there are pluses and minuses here to both of these ways. I think the initial condition plus method is faster. It's especially faster if we have our calculator. If we have our calculator, we don't even have to do an indefinite integral and solve for c. But by hand, these two took about the same amount of time each. If I needed to find a whole bunch of capital F values, then solving for c would be the method to go, right? Because if I wanted to do, okay, well, what's f of 5? Well, I already have capital F of x. I can just plug in and solve for 5, right? I can plug in for anything and solve for it. So if you have to find multiple things, c might be the way to go. But I prefer initial condition plus. This comes up a lot on the calculator multiple choice, and they're very fast, easy questions if you remember initial condition plus. Let me show you just one more example with initial condition plus when I just use a slightly different notation. So here's what we know. I know that f prime of x equals 2x cubed plus 1. Okay. I want you to find f of 2 given that f of 0 equals 10. Okay? So the difference in notation here is I'm not using lowercase f and cap f. I'm using f prime and f. Okay? But the relationship we need to know here is if I'm looking for f of 2 and the function I know is f prime, to go from f prime back to f, I know I have to be integrating here. Okay? To figure out f of anything, I need to find the integral. But remember, there are infinitely many antiderivatives, right? So we need this f of 0 equals 10 is absolutely vital for us solving this problem. In fact, if I don't give you f of 0 equals 10, there's no way that you can solve this problem. It's impossible. So again, what I want to look at are our a and b. The one that you have a value for, right? The f value in this case that you know, that x value is a, the one we're looking for is b. So here's what I know, f of a, which is 10, plus my integral from a to b of 2x cubed plus 1 dx must be my answer that I'm looking for, which is f of 2, right? So again, f of 0 plus the integral from 0 to 2 of f prime of x dx equals f of 2. Now all I have to do is crank this thing out. And what I don't want to do is forget to keep writing this 10 plus. This thing's ready to antiderive. And I get half x to the fourth plus x as my antiderivative from 0 to 2 equals f of 2. Okay, now I got 10 plus. Now I'm going to plug in 2. And I'm going to plug in 0, which is really nice here because it's 0. That's going to equal f of 2. 2 to the fourth is 16. 16 divided by 2 is 8. So I got 10 plus 8 plus 2. 8 plus 2 is 10. 10 plus 10 is 20. And I know that f of 2 is 20. Okay. I want you to get in the habit of using both initial condition plus as well as solving for C. Okay? Again, if I solve this thing for C, here's what I would know. I know that f of x has to equal the antiderivative of f prime of x. So I'm just going to solve this again, and I should get 20. Right? F prime was, what was it, 2x cubed plus 1? So my antiderivative here is half x to the fourth plus x plus c. Right? I know that's true. And what I do know is that f of 0 equals 10. So plugging in 10 for my y value and 0 for my x value tells me that I get a c value of 10. So I know that the function f of x is half x to the fourth plus x plus 10. Now solving for f of 2, I can plug this in and get, again, 2 to the fourth is 16, divided by 2 is 8. 8 plus 2 plus 10 equals 20. So I'm going to get 20 either way here. I prefer using initial condition plus to solve it, but just showing you that that's, when we're talking about, why do we do the plus C? This is why the plus C matters, right? It allows us to plug in to solve for that C. But in order to know it, we have to know that initial condition point. Okay, that's it. I'm going to cut it there. That's it for today. Have a good one. Talk to you guys later. 2 chains. Bye.